Hello.
Hello.
Morning. Morning. All right. Well, let's get started. So, yeah, we had a DeVore meeting this week. We talked about some papers and projects that are being proposed for Google Summer of Code. So that's good. We didn't have any other meetings, but I got a message from Jesse saying that he's interested in restarting both the Cognition Futures meeting and the Cybernetics meeting. So we'll see how that goes. So maybe starting that back up. And then additionally, I'd like to start the open source meetings back up. I'm not sure when we're going to start doing that. Probably towards the end of this month, because we're coming up on our traditional start of the Google Summer of Code program. So that's I don't know what date that might be. Maybe in about 2 weeks or so. So stay tuned for that. And in the summers we do our open source meetings. It's usually every week on Fridays, and I'll send out an alert to set the final time. It's usually in North America. It's usually morning to mid afternoon. So we'll do that. We usually have like reports on different projects, some topic that we talk about, and we have, and on our YouTube channel, we have a playlist for past years where we've done this. So usually the open source meeting is seasonal. It goes from the beginning of May to probably September or October. And that's largely when we can have reports on summer projects. We'll go through a number of topics that I think are useful to a lot of people. And, it's a good way for people in the lab and even outside the lab to get involved in open source. We also add an open science component into it from time to time. And it's quite a good experience. So I will be in touch in terms of when that will start. So let's start off. Actually, I want to go through some stuff from the Slack. So this is a paper that Vidhi posted in, I believe, Cognition Futures. So this looks interesting, and I'd like to cover it. So this is an arXiv paper on meta-learned models of cognition. 2 weeks ago, last time we met, we talked about meta-learning and meta-learning models. So this is meta-learned models of cognition. And it looks like it's a group from the Max Planck Institute and DeepMind. And so I guess they're going to talk about meta-learning and how that can be used for learning and cognition. So let's go over the abstract first. The short abstract is that meta-learning has established itself as a promising tool for building models of human cognition in recent years. Yet, a coherent research program around meta-learned models of cognition is still missing. The purpose of the present article is to develop such a research program. We accomplish this by pointing out that meta-learning can be used to construct Bayes optimal learning algorithms, allowing us to draw strong connections to the rational analysis of cognition. We then discuss several advantages of meta-learning, the meta-learning framework over traditional Bayesian methods, and re-examine prior work in the context of these new insights. So this is sort of putting meta-learning in contrast with Bayesian methods, which I find interesting. I guess they're using Bayesian methods, but not in the same way. So if we're thinking about Bayesian methods, this is where we have a set of conditional probabilities, where we have an a priori distribution, and then we have a set of observations, and then we look at how that a priori distribution matches the current observation, and we update our priors to reflect that new information, and we converge upon a solution. So that's where they're going. So the long abstract is meta-learning is a framework for learning algorithms through repeated interactions with an environment, as opposed to designing them by hand. So hand coding. In recent years, this framework has established itself as a promising tool for building models of human cognition. Yet a coherent research program around meta-learned models of cognition is still missing. The purpose of this article is to synthesize previous work in the field and establish such a research program. So they rely on three key pillars. The first is to point out that meta-learning can be used to construct Bayes-optimal learning algorithms. The result not only implies that any behavioral phenomena that can be explained by a Bayesian model can also be explained by a meta-learned model, but also allows us to draw strong connections to the rational analysis of cognition. So, we want to be able to understand sort of behavioral phenomena, but we also want to be able to have this rational analysis of cognition. So we want to be able to explain behavior by meta-learning and have a theoretical framework as well. We then discuss several advantages of meta-learning framework over traditional Bayesian methods. So we're using Bayesian methods, but we're using this specific class of Bayesian method. In particular, we argue that meta-learning can be applied to situations where Bayesian inference is impossible, and that it enables us to make rational models of cognition more realistic, either by incorporating limited computational resources or neuroscientific knowledge. So this is where we have, we go beyond sort of the classic cases of Bayesian inference, and we can make, so rational models of cognition typically, sort of are divorced from reality in some ways. And so, a lot of times people do things that are irrational or they don't make the optimal solution. And so, with this kind of meta-learning framework, you can actually kind of make up the ground between the rational analysis of cognition and the real world. So, again, how do you make this more realistic? You either incorporate limited computational resources or neuroscientific knowledge. So this is where we know things about decision making that go beyond sort of a rational analysis of behavior, or we build a computational model. Finally, we re-examine prior studies from psychology and neuroscience that have applied meta-learning to put them in the context of these new insights. In summary, our work highlights that meta-learning considerably extends the scope of rational analysis, and thereby of cognitive theories more generally. So this is a nice paper. I think it's kind of really presenting this area as sort of a Bayesian, putting it squarely in the Bayesian camp, but also kind of drawing out how meta-learning can contribute to theory. So this talks about meta-learned models of cognition and how it's a sort of computational model. So it's hard to imagine cognitive psychology and neuroscience without computational models. Traditionally, such models have been hand-designed by expert researchers, and it's usually people propose a computational model of like memory or attention or something like that. And so this has led us to cognitive architectures, where we provide a fixed set of structures and a definition of how these structures interact with each other. So usually like a flow diagram or some sort of model, like Bayesian model, where you have, conditional probabilities, conditional variables, things like that. In Bayesian models of cognition, researchers instead specify a prior and a likelihood function, which, in combination with Bayes' rule, fully determine the model's behavior. So this is this reference, Griffiths and Tenenbaum, 2008, where they talk about Bayesian models of cognition. The framework of meta-learning, and these are the citations here, offers a radically different approach for constructing computational models by learning them through repeated interactions with an environment, instead of requiring an a priori specification from a researcher. So this is where you don't have these top-down models, you have these bottom-up models. So they basically are emergent, or they're generative, in the sense that they produce sort of, different mechanisms and different interactions. So this is a little bit different approach than the traditional cognitive architecture approach. So psychologists have started to apply meta-learning to the study of human learning. Meta-learning models can capture a wide range of empirically observed phenomena that could not be explained otherwise. So they're able to reproduce human biases in probabilistic reasoning, discover heuristic decision-making strategies used by people, and generalize compositionally on complex language tasks in a human-like manner. So basically, you have these types of things that are sort of kind of go beyond the rational analysis of behavior, where you don't always assume that people pick the sort of most optimal choice. You also introduce human biases, so you want to be able to reproduce these things to successfully model them. The goal of the present article is to develop a research program around meta-learned models in cognition, and in doing so offer a synthesis of previous work. So to establish such a research program, we will make use of a recent result from the machine learning community, showing that meta-learning can be used to construct Bayes optimal learning algorithms. This correspondence is interesting from a psychological perspective because it allows us to connect meta-learning to another already well-established framework, which is irrational analysis of cognition. So in a rational analysis, one has to first specify the goal of an agent, along with a description of the environment that the agent interacts with. The Bayes optimal solution for the task at hand is then derived based on these assumptions and tested against empirical data. If needed, assumptions are modified and the whole process is repeated. This approach for constructing cognitive models has a tremendous impact on psychology because it explains, quote, why cognition works by viewing it as an approximation to ideal statistical inference, given the structure of natural tasks in an environment. So we have, ideal statistical inference. We can assume that things are optimal. We could build a statistical model or some sort of computational model and make predictions. But in terms of what we're doing here, we want to see if we can build approximations. So we don't want to build exactly that. We want to come nearby. The observation that meta-learned models can implement Bayesian inference implies that a meta-learned model can be used as a replacement for a corresponding Bayesian model in a rational analysis, and thus suggests that any behavioral phenomena can be captured by a Bayesian model, or any phenomena that can be captured by a Bayesian model can also be captured by a meta-learned model. So there's this equivalence between the Bayesian model and the meta-learned model in terms of expressivity. The question is which one is better, and what they're arguing is that the meta-learned model, being a class of Bayesian models, is actually better than a standard Bayesian model. So they start with these 4 arguments. So they sort of ask, why do we need to go beyond the Bayesian approach? And so they have this figure 1 has the 4 arguments in it. So the first argument is that possible, even if exact, Bayesian inference is computationally intractable. So this is obviously this computer is struggling with the answer. So this is where we can sometimes model things and frame and formulate them in terms of a mathematical or computational model. but we can't actually get a good solution or run it to an exact solution. So, sometimes there are problems that are computationally intractable where it takes way too long to get the optimal solution. And that may hold true maybe for the brain as well as a computer. But it's better to have these heuristics. Isn't this, in fact, that's the argument kind of for cognitive heuristics, is that we can't have perfect information about the world. So we have to generate these heuristic solutions to problems, to decision-making problems. And so those are good enough to get us through the world, and that's what matters. So that's kind of their point, argument one. Their argument two is that possible even if impossible to phrase, or it's possible even if it is impossible to phrase the corresponding inference problem. So this is here, meta-learning can produce approximately optimal learning algorithms, even if it is not possible to phrase the corresponding inference problem in the first place. So we want to be able to get an approximation, this first argument. And the second argument, meta-learning can do this for us. And, even if it's really hard to sort of state what the problem is. So sometimes it's that we know what the problem is, but we can't solve or find the exact solution. In other cases, it's hard to even pose the problem correctly. So there's, I think in the past, people have phrased different types of problems as ill-posed problems. So I think moving an arm to a target has been phrased as an ill-posed problem because there are too many open parameters and you have to specify them. And so these are, kind of where you have things in the world that pose problems to, say, cognition or a cognitive system. It has to solve them, but it also has to understand what it's doing. And a lot of times you have these open systems, or you have sort of like an open frame of adaptation, where if I perform one activity, whatever I do in that activity is contingent upon the next activity and so forth. So, this is the kind of thing for argument two. It's not saying that it can't find the solution. It's saying that even the problem is ill-posed. Okay, so, and then they show this in terms of a probability distribution. So if you have probability of H, what goes into the probability of H? Or the probability of D given H, what goes into that probability? Okay. Argument three, meta-learning makes it easy to manipulate a learning algorithm's complexity and can therefore be used to construct resource rational models of learning. So this is, again, this one, argument three, makes it easy to manipulate a learning algorithm's complexity. So this shows you have a neural net, and you're pruning the neural net to find a solution, or you're finding the weights for it. Meta-learning can do this. And then figure four, meta-learning allows us to integrate neuroscientific insights into the rational analysis of cognition by incorporating these insights into model architectures. So this is argument four, integrates neuroscientific insights into the rational analysis of cognition. This is where we have a model of something happening in the brain, like we might describe the process of short-term memory or spatial cognition. And we have a number of places where this happens and pathways. And then we can basically say if these things happen, given those things, then we have a probability of something else. So probability of H given D is, according to Bayes' rule, this conditional probability that if one thing happens, another thing will happen. We know from the brain that the brain is processing this, so we kind of know what those probabilities might be. Okay, so the first 2 points highlight situations in which meta-learned models can be used for rational analysis, but traditional Bayesian models cannot. So these two kind of are more where meta-learned models can be used for rational analysis, The latter 2 points provide examples of how meta-learning enables us to make rational models of cognition more realistic in these cases, either by incorporating limited computational resources or neuroscientific insights. Okay. So they kind of talk about meta-learned rationality, what that is. So the prefix meta is generally used in a self-referential sense. So meta rules are rules about rules. Meta-learning consequently refers to learning about learning. We therefore need to first establish a common definition of learning, and so they use this definition from Mitchell, circa 1997. So this is for a given task, training experience, and performance measure. An algorithm is said to learn from its performance if its performance at the task improves with experience. So any kind of well-defined task, sometimes it can be an ill-defined task. Someday you have to have some sort of measure of it, and you have to have it presented as an experience. So you have to have the task presented over and over again. The algorithm is said to learn if the performance of the task improves with experience. So you have to have some improvement, which gives you a learning rate, which derives from the amount learned over the time over the repeated exposures and the repeated measurements. So that's what we mean by learning. Then we can talk about the Bayesian inference for rational analysis. So in a rational analysis of cognition, researchers are trying to compare human behavior to that of an optimal learning algorithm. However, it turns out that no learning algorithm is better than any other when averaged over all possible problems. And this is a finding that's reported in the literature, which means that we first have to make additional assumptions about the to-be-solved problem to obtaining a well-defined notion of optimality. Okay, so for our running example, one may make the following somewhat realistic assumptions. And so they're giving an example here of a problem domain. So the first thing is each observed insect length is sampled from a normal distribution with a mean and a standard deviation. So basically you're observing a bunch of things that are the same. You're measuring insects, you're measuring their length. So the measure is sort of a standardized thing. You make a bunch of observations on insects. You then put that make a normal distribution from that. You assume some normality with a mean and a standard deviation. Okay, so that's the first point. That's the set of observations. Number two is that an insect species mean length, mu, cannot be observed directly. So we can't observe the mean directly. We can measure all the insects we want, but we'll never observe the mean directly. We only know that there's a distribution, there's a standard deviation of 2 centimeters, and if we build the statistical model, we can find the mean. But the mean isn't something that's inherent in nature. We only know the standard deviation and then the mean derived from a model of the data, of the observations. Number three is that mean lengths across all insect species are distributed according to a normal distribution with a mean of 10 centimeters and a standard deviation of 3 centimeters. So we know what this distribution looks like when we get enough observations. We know kind of what the standard deviation should be because people have observed this before in different insects. You model insects of a certain species. You're not always measuring the same ones. You're just kind of measuring all different instances, and you derive that from previous observations. And then your current set of observations has properties that either come close to matching that or don't. So usually what we get is we get this mean that we derive from our measurements. We also have a mean that we've observed in the past. We have a standard deviation that's been known in the past. And then we have the standard deviation that we can measure. So those are the assumptions. An optimal way of making predictions about new observations under such assumptions is specified by Bayesian inference. So we need to have a prior distribution, p mu, that defines an agent's initial beliefs about possible parameter values before observing any data and a likelihood P x 1 over t given u, which captures the agent's knowledge about how data is generated for a given set of parameters. So we know that, we know what the prior distribution is. We also know, that they're going to be this set of observations, and that there's a likelihood about this generative process. In our running example, the prior and the likelihood can be identified as follows, right here. And then where x1 to t denotes a sequence of observed insect lengths, and the product equation 2, which is up here, arises due to the additional assumption that observations are independent given the parameters. You can see that this is a summation here of all of these, the distribution, or the observations given the prior distribution. I guess it's the multiplication, not the summation. Okay, so the outcome of Bayesian inference is a posterior predictive distribution, which the agent can use to make probabilistic predictions about hypothetical future observation. To obtain this posterior predictive distribution, the agent first combines prior and likelihood into a posterior distribution, and that's here. In the subsequent step, the agent then averages over all possible parameter values weighted by their posterior probability to get the posterior predictive distribution, which is here. So you can, build Bayesian models that are pretty complex. Multiple arguments justify Bayesian inference as a normative procedure, and thereby its use for rational analysis. This includes Dutch book arguments, free energy minimization, and performance-based justification. So they put free energy minimization in this class of rational analyses. And, it's connected to Bayesian inference. For this article, I'm mainly interested in the latter class of performance-based justifications, which is this last category here. As we will demonstrate, meta-learning algorithms can be derived to learn approximations of Bayesian inference. Performance-based justifications are based on the notion of frequentist statistics. Particularly relevant for this article is a theorem proved by Atchison. It states that the posterior predictive distribution is the distribution from the set of distributions that maximizes the log likelihood of hypothetical future observations when averaged over the generating distribution. So this log likelihood is the thing that you get out of a Bayesian distribution, and that's what we're dealing with here. Frequentist statistics often deals in probabilities instead of likelihoods. That's the difference usually between the two. This implies that if an agent wants to make a prediction about the length of a still unobserved exemplar from a particular insect species and measures its performance using the log likelihood, then averaged across all possible species that can be encountered, there is no better way of doing it than using the posterior predictive distribution. So they give a short proof, and they get through some of the technical details here. So they kind of get into the Bayesian argument. They get into these kind of models, these performance-based justifications, and they show that the Bayesian approach is better. This log likelihood approach is better than a frequentist approach. Okay, now we get into meta-learning. So that's a long kind of introduction into meta-learning, thinking about sort of Bayes optimal learning and how that works. So now, of course, when you're learning about learning, you can see the kind of connection here. You have a prior distribution, which is like learning, and then you have some set of observations about learning. So you have a conditional probability, which is learning about learning. Hold on. So that's, I think, where they're going with this. So formally speaking, a meta-learning algorithm is defined as any algorithm that uses its experience to change certain aspects of a learning algorithm or the learning method itself, such that the modified learner is better than the original learner at learning from additional experiments. So you're basically modifying the learning process by learning about learning, and it's improving your performance. All right, so to accomplish this, one first decides on an inner loop learning algorithm and determines which of its aspects can be modified. We also refer to these modifiable aspects as metaparameters. In an outer loop or meta-learning process, the system is then trained on a series of learning problems, such that the inner loop learning algorithm gets better at solving problems that it encounters. Okay, so this is basically showing this process in figure 2. So you have learning. Of course, we talked about this measurement problem, and this is a butterfly instead of, I guess, a metamorphized insect here. You're measuring parts of its phenotype. You're getting these measurements. You're getting a distribution of measurements. The base learner learns about these measurements, and then you have the mean of the measurement. So that's a performance measure. And so, okay, let's go over. So that's in the learning rectangle. And then the meta-learning rectangle is where these things get passed in and out of the learning algorithm. So you're modifying learning by introducing new instances, new species of insect. And so you have measurements for those. So it's able to learn different types and instances. And, that's modifying it in terms of the training. You have metaparameters which affect the base learner. So you have parameters that affect how it's able to sample from that original distribution or the Bayesian rule it's using, the structure of that rule. And then you have performance measures. So the performance measures feed back to the metaparameters. So if it's doing a particularly good job of distilling the learning rule, then those metaparameters are reinforced. If not, they're changed. So figure 2 says high-level overview of the meta-learning process. A base learner, the green rectangle and this green rectangle here, receives data and performs some internal computations that improve its predictions on future data points. A meta-learner in the blue rectangle, which is this outer rectangle, encompasses a set of metaparameters that can be adapted to create an improved learner. This is accomplished by training the learner on a distribution of learning-related problems, which are these things here. Okay. So this talks about kinds of things that you can meta-learn. You can meta-learn hyperparameters for a base learning algorithm, such as learning rates, batch sizes, or training epochs. You can meta-learn initial parameters of a neural network that is trained via stochastic gradient descent. You can meta-learn prior distributions in a probabilistic graphical model. And then you can meta-learn entire learning algorithms. So they're making some pretty good claims about what can be learned here, or meta-learned, I should say. So in terms of meta-learned inference, it may seem like a daunting goal to learn an entire learning algorithm from scratch, but the core idea behind the approach we discuss is the following. And the following is a surprisingly simple idea. Instead of using Bayesian inference to obtain the posterior predictive distribution, we teach a general purpose function approximator to do this inference. So previous work is mostly focused on using recurrent neural networks as function approximators in this setting, and thus we will, without loss of generality, focus our upcoming exposition on this class of models. Like the posterior predictive distribution, the recurrent neural network processes a sequence of observed length from a particular insect species, as we saw in the figure. It produces a predictive distribution over the lengths of potential future observations of the same species. More concretely, the meta-learned predictive distribution takes a predetermined functional form, whose parameters are given by the network outputs. So for example, if we decided to use a normal distribution as the functional form of the meta-learned predictive distribution, outputs of the network would correspond to an expected length and its standard deviation. So this is what we see in figure 3 here. So we have the meta learning setup where we have these parameters, we have forward and backward in this. So we have x1, x2, and xt. So every time we kind of get an observation, we make the comparison, and then we end up with this log likelihood. Then there's, we can put this into pseudocode. Basically, we see if the algorithm converges by sampling the sample data and going forward and getting to a point where that log likelihood is optimized. Then we have meta learning loss. So we try to match a Bayes optimal level of meta learning loss. We go from a very high loss over many iterations of the algorithm, and we try to converge upon the Bayes optimal loss. And then the predictive distributions show for insect length, if we have our meta-learned example and our Bayesian example, over time, over a number of iterations of the algorithm, we should converge upon the Bayes optimal solution. So here on the left, we have the probability density versus insect length. The Bayes optimal model predicts a mean insect length of about 9.5, and then the meta-learned model at about 0. That's in T0, so this is when it's just observing it for the first time. If we keep running this algorithm over and over, and we get information from each observation, and we keep optimizing the log likelihood and reducing the loss, we end up converging upon the mean so that we end up with around the same mean as the Bayes optimal condition. So that's basically what it does. So it's learning an algorithm, and then it says how good is a meta-learned algorithm, and this is where they evaluate their work. So they basically, they try to do this sort of evaluation. I mean, they don't give any statistics here, but they kind of suggest that it can be done using our standard tools. So we have previously shown that the global optimum for equation 7, which is up here, is achieved by the posterior predictive distribution. Thus, by maximizing this performance measure, the network is actively encouraged to implement an approximation to exact Bayesian inference. To perform an inference, we simply have to query the network's outputs after providing it with a particular sequence of observations. So this is basically where we're observing each observation, we're kind of adjusting the algorithm. If we want to use the fully optimized network for rational analysis, we have to ask ourselves, how well does the resulting model approximate Bayesian inference? So we have to consider two things. First, the network has to be sufficiently expressive to produce the exact posterior predictive distribution for all input sequences. That means that we have to have some sort of network representation of this broad distribution. And, if we can't produce that posterior predictive distribution, we need to be able to adapt or evolve the network in a way that shapes that. So that's why we go through all these different iterations of the log likelihood of this posterior predictive distribution. Neural networks of sufficient width are universal function approximators, meaning that they can approximate any continuous function to arbitrary precision. So the aspect is not too problematic for the optimality argument. However, in the second aspect, we can assume that the network is powerful enough to represent the global optimum of equation 7. The employed optimization procedure also has to find it. So if we can represent the global optimum, we have to be able to find it. So we have this aspect of expressibility, and then we have this aspect of finding something or finding the optimum. While we are not aware of any theorem that could provide such a guarantee, in practice, it has been observed that meta-learning procedures similar to the one discussed here often lead to networks that closely approximate Bayesian inference. We provide a visualization demonstrating that the predictions of a meta-learned model closely resemble those of exact Bayesian inference, for insight length example. So basically, they're able to, they frame kind of these two aspects. And so this has strengths and weaknesses. But we can do things like we can, look at supervised learning as we did here. We can also extend it to the reinforcement learning case as well. So in summary, it is possible to meta-learn an approximately Bayes optimal learning algorithm. If exact Bayesian inference is not tractable, such models are our best option for performing rational analyses. Yet, many other methods for approximate inference, such as variational inference and MCMC methods, which are Monte Carlo methods, Monte Carlo methods, also share this feature and will thus ultimately be an empirical question of which of these approximations provide a better description of human learning. So again, this is where, this is kind of, I just went through argument one here. And I think I spent a lot, maybe too much time on it because there are other aspects here. So the number two, I'm just going to point out is these unspecified problems where you really have sometimes these ill-posed problems where, you really need to be able to specify a prior and a likelihood, and sometimes you can't do that. So this is where, again, we have, even in the world of Bayesian decision theory, we have these small and large world problems. The small world problem is one in which all relevant alternatives, their consequences and probabilities are known. On the other hand, a large world problem is one in which the prior, the likelihood, or both cannot be identified. So you have this distinction between things where you can know all of these things and problems where you can't identify any of them. Savage's distinction between small and large worlds is relevant for the rational analysis of human cognition, as its critics have pointed out that Bayesian inference only provides a justification for optimal reasoning in small world problems, and that very few problems of interest to the cognitive, behavioral, and social sciences can be said to satisfy this condition. So basically, most of your problems in cognitive science don't satisfy this condition. So we need to be able to make some assumptions and make them correctly. So this is kind of saying that this is meta-learning is possible in theory, but to become a good tool, we need to be able to make good estimates of different things in the world. So, and this is, of course, relevant to artificial intelligence where, or in continual learning, where you have this thing where you have to kind of engage in the world in real time, and you don't know what you're going to find, and sometimes you don't know the parameters of the problem that you're trying to solve. So that's kind of getting at that point. Then they have argument 3. They phrase that in terms of resource rationality, and then argument 4 in terms of neuroscience. And so this kind of talks about how we have networks of spiking neurons and the way that they are able to learn behavior. And it kind of extends this to reinforcement learning at this point, because that's kind of the natural connection between neuronal networks and inference. Okay, so that's a very good paper. It's very long, and I'm not going to go over very much more of it because I think we spent enough time on it. Do we have any comments about this?
Can you hear me okay?
Yeah.
I got a camera for my Linux box, so
yeah.
I wanted to stop looking at my iPads.
Yeah.
While anyway, yeah. Well, we're gonna see a lot more of this. Is my comment, and they who's the Google DeepMind guy? David Silver. David Silver had a interview. I hesitate to call it a talk. A SciComm interview with Hannah Fry. So like DeepMind hired Hannah Fry to be their science communicator.
Yeah.
I don't know if you've seen this. Yeah. And anyway, he was talking yesterday or the day. He was talking this week about the age of human human knowledge derived AI is coming to a close, and what will power the next wave is basically this. I mean, or is basically kind of meta learning, right?
Yeah.
Allowing the computer to form its own experiences and allow the algorithms to form their own experiences. That's what it just made me think of.
Right.
His discussion of this, and this seems to be kind of trying to be an example of that. It's not much of a comment.
Why do you think we'll be seeing a lot more of it?
Well, I mean, his point is it's really just expanding on his point, or summarizing his point that part of it is a slam on large language models, right? That yes, okay, you've trained on all extant text, and you've derived this artifact from what can be contained in language structure, right? as well as knowledge, right? However, reasoning and things like that have become a secondary goal, which you see with DeepSeek and one and these the things we've covered recently, right? And perhaps people who decide trade wars on the basis of ChatGPT and use algorithms that that the models really just don't understand. Right?
Yeah,
like they don't get what they're doing. He was trying to make the point that humans really value the knowledge that they've put together, in the sense of like they think that this is valuable,
yeah,
and kind of pinnacle. But he's trying to make the case that the problem with current levels of AI is that they're not their own learning systems. They're not learning how to learn. I think is kind of his case.
yeah.
And if we focused on having them learn how to learn, then they would be able to generate their own kind of knowledge stores through these kinds of interactions, right? Or through interactions, they would create these knowledge stores, and they would I think he was trying to say learn like babies.
Yeah. Everyone says that now.
He's not. I've never seen in his work the same kind of not respect. I'm not sure the word, but emphasis that you see with like Josh Tenenbaum. on developmental, childlike activities.
Yeah.
But I think he has the Kenneth Stanley kind of curiosity, respect.
Yeah.
Yeah.
I don't know if Vidhi or Sarrah had any thoughts on those.
Like current AI systems are not thinking on their own. I heard that resonated with me a bit, because even I've read a lot of these things recently of how like the next generation of AI or AGI is just supposed to be that, like it's like, because everything that is now is just it's reproducing information in a way, and we are hoping that the next what we are able to do is actually able to create something. But I haven't seen anything in the current state of the art where it has happened yet. So yeah, I mean that part I agree on.
Right.
So, yeah, that's about it.
Yeah. I think in this paper they're showing that there's sort of this, there's this supervised learning where you might have labels and things that you can measure, and you have an easily defined problem, and then you have this other algorithm that's kind of learning about that process instead of from the data. It's kind of optimizing that process. And so, it's kind of like if you learn something for the first time, and then you reflect on it. I mean, that's, I guess, what they're trying to replicate. And then when they do that, they get a better result. It's a more refined result. So if I think of I can learn things, I can observe data, I can use this sort of posterior log likelihood. I mean, I don't do that, I don't state it, but that's the idea in these computational models, is that I'm doing that calculation, and then I'm learning how to optimize my learning process. Now, the question, of course, is that a realistic view of, say, like human learning? You could have it for machine learning, and it works to some extent, but then the idea of it, does learning actually work that way? Because a lot of our machine learning models are drawn from human models and other animal models, but mainly human models. And so the question is, do we actually do that? Or do we do something analogous to that? In other words, we use something as compact as a log likelihood calculation and use that to sort of optimize our learning. Do we even reflect upon all learning? Because we might reflect upon, learning if we're if we're learning the lyrics to a song, reciting it. But if you're learning something like how to ride a bike or do some sort of procedural learning, that may not always be the case. You might have this different type of, make this different type of calculation. But I don't know. It's a good question. So that's the criticism, I think, of a lot of, or would be the criticism of any meta learning model, is, I guess we kind of agree that we kind of reflect on what we learn, or what we're exposed to, but is that really something that benefits learning to the extent that the meta learning model suggests? In other words, is it important to reflect on something, or is it just important to be able to consolidate your learning over time, which means you might sleep on it and then dream about some procedure, like if you're trying to trace a route out in your head and you consolidate that knowledge. So that's, is that reflection? Is that meta learning, or is that just consolidating all of the data that you've gathered and building a model of it? It's hard to say exactly what metaphor is best.
Yeah. But you'd agree that it's the developmental psychologists that think about this the most.
Okay.
Or well, I mean, not maybe only, right? But again, the differences between language learning in infants, learning to ride a bike, learning to, like as a kind of like separate kind of skill, like what algorithms go into that, and it's probably hybrid.
Yeah.
Like it's probably mixtures of systems, right?
Right. Yeah, yeah, and then tying it back to the neuroscience, of course, what structures are being used in learning, and depending what you're learning, it's different systems. But then what's the meta learning for each system? So like procedural learning uses a certain set of structures. Maybe like declarative learning uses another set of structures, and then those meta learning processes would be different. And you might want to merge those two types of learning. So that's maybe a third meta learning process.
Yeah. I mean, I think there's a hint in at least Silver's presentation that, of course, machines might have not a better way. Like machines might do it differently.
Right. Well, yeah.
And so in other words, giving them an algorithm that does meta learning is what they need.
Yeah.
I mean, there is. Yeah. I mean, I'm sure it's too simplistic.
Right.
But
so
I'll try and find a link to that, just so that
Yeah.
So yeah, the other thing here, of course, then is continual learning, and it's linked to that. So continual learning is where you're doing some naturalistic process or some naturalistic learning, which means you go through the world and you explore, and you don't have these trial by trial presentations. So if you're building a prior distribution, it's from maybe like isolated observations, or it's sequences of observations that overlap, and you're getting these, and you may have multiple prior distributions depending on where, what you're doing and where you are. And so it's a lot harder to kind of use that kind of meta learning model in this case, because you're not only having to take these naturalistic streams and segment them and figure out, what I'm learning about something by interacting with it at different time scales, different instances. It seems like a lot richer data, but at the same time, it's harder to sort of integrate into a model. And then how do you learn about that? Like, how do you do that in real time? Because you have to do that in real time. You can't take the learning experience offline and then learn about it. So, I mean, I guess they did show like that there's a sort of continuous structure, at least to some extent, in the Bayesian case, where they have like each observation is updated and then keeps getting updated as it contributes to that prior distribution. But that can lead to a lot of fluctuations in performance early on, right? If you kind of observe only a couple of instances of something, your performance is going to be really weird until you get down to like some, maybe aggregating maybe 100 or 1,000 observations. As you saw in the loss graphs, you have like the optimal Bayes, which is flat, which is kind of your control, and then you have this meta learning system where it starts with a very high loss and then it kind of converges down. But that takes a while to do. And I was thinking, in the continuous case, you're going to have this problem where you're observing things in the world maybe for the first time. You're trying to make sense of them. And so that loss is very great for a while, and then it kind of settles down. And I mean, that might be expected. I mean, that's kind of maybe what we're doing in development too, is, we have this, I guess I don't want to call it a loss rate, but like, it's like an error rate maybe, or like a category error. rate. And it goes down as we learn more about things. But that category error, though, that error rate, when it's high, it can provide opportunities for learning in and of itself, because there are a lot of things that you can put together from making errors. A lot of creativity. So it's very interesting how machine learning kind of does its own thing in a lot of ways. Like, it has to, because you're building things that are doing things that are separate, like very different from human cognition a lot of times. So that was a great, Vidhi. That was a good paper. And yeah, it's definitely an interesting area of research. So this is YouTube video for what?
That's just the David Silver.
Okay. All right, so let's move on. Last time we talked about, actually we were talking about continual learning or continuous learning in humans. And I was talking about this time course that we use in like doing single trial observations. So this is a network here. It's a kind of a embodied neural network, because it deals with not just the brain, but the spinal cord and the peripheral nervous system as well. And so this child is interacting with a video game console, and this is showing the different parts of the nervous system, both central and peripheral, and where things are happening at what time scales. So remember I said that there are these time scales. We have like the millisecond time scale, and then we have the minute time scale and the hour time scale. And so like this is one kind of slice or snapshot of this child interacting with this console. They're taking in a visual image in 20 to 40 milliseconds. That visual image is being relayed through the retina. It's going down to V1 at 60 to 90 milliseconds. And then it's going back forward to the inferotemporal cortex at 150 milliseconds. It's going to prefrontal cortex at 180 milliseconds. So this is like a signal or the information that's being relayed. And these are kind of the estimates of when the information arrives in a certain anatomical location. Then, prefrontal cortex at 180 milliseconds, then medial cortex at 220 milliseconds. And then, of course, it goes back down to the spinal cord, and then it goes to the fingers at 280 to 400 milliseconds, where that information then tells the fingers what to do. So you go from like seeing something on a screen, processing what that is, making maybe a prediction about what to do next, and then sending a command signal through the spinal cord to the fingers, and then there's a button press. Now, this is, of course, we could make a shortcut here with a brain-machine interface. We could record the signal in the MC, and then have a prosthetic that does a button press for us. So that if we can interpret that signal properly, then we can make that, we maybe can shorten that a little bit. Or, if you don't have fingers to use, we can correctly interpret that signal and produce an output. So there's this closed loop between the screen and then the controller, and the human is in the loop, basically. And so that's kind of what this is describing. Now, when I talked about last week is that, you have this, you can imagine this child playing with this console for maybe 40 minutes. And so at each point, this is just representing one instance, which is like one kind of unit of action. Where you see something on a screen, you respond to it, you use your finger to respond to it, and that's like one instance. And of course, this happens many, many times over the course of the gameplay, which is like 40 minutes. This is, and information is not only getting routed through these centers, but it's accumulating. Furthermore, you have this sort of refractory period and this adaptation in these regions, where if, there's enough information that goes through there over time, it starts to adapt to that information. It starts to make things more optimal in terms of the flow of the information, but it also starts to have these sort of collective effects that can have, that can change how that information is processed over time, almost like these avalanches of effects. And so if you think about learning, if you're playing the game and you're responding to things kind of in the immediate now, eventually that experience will build up and you'll kind of maybe figure out how to do something, make a shortcut in the action of the gameplay. And that changes how your fingers move, that changes how you process the information. We know from learning that sometimes, the processing of information speeds up with learning. Sometimes we have interference with learning. There are all these effects that we can describe that happen at a higher time scale than what this is showing. So I just wanted to go back to this to kind of cover what we had talked about last week with that timeline and what that looks like with the brain, what that looks like with these closed loop action systems and so forth.
Well, and just to also add, trying to capture that millisecond, millisecond by millisecond,
right,
is a big part of why people still use EEG.
Right.
I mean, like trying to capture that with fMRI is you end up doing focusing on kind of one part of that or something like that, so that you can deal with the kind of temporal the temporal scale that you're collecting data, but you can capture that millisecond by millisecond transfer and back and forth, and closed loops and recurrence with EEG.
Oh, yeah. So I mean, and that's of course the way that they do a lot of brain-computer interfaces. They use some sort of electrophysiological measure. Sometimes they'll use FNIR, but sometimes you're trying to get a signal like if this area is activated or not, and that's kind of so you can But the point here is that like that activity will change over time, and you're measuring this sort of dynamic set of signals, and there's all sorts of effects that happen over longer time scales. So, but yeah, you get the measurements of that kind of process from electrophysiology, EEG specifically. So yeah, that was this point here. But I'm trying to make a broader point here, which is that this is in the human brain. And of course, if we think about primate brains, it's a little bit different. And then we go farther out and we start to get into different, brains with different features. And so this process of interacting with the stimulus is much different. So this brings us to this, let's see. Okay. This brings us to this article here. So this is from Quantum Magazine. And this is, it says, intelligence evolved at least twice in vertebrate animals. So this is talking about how invertebrates, which is anything from fishes to mammals, like birds and amphibians, in the mix. And that includes a lot of different taxa, a lot of different species. We see at least twice that in different forms of intelligence have evolved. So we see this we see one form of intelligence in mammals, and then we see another form of intelligence in birds. And what we mean by a form of intelligence is that it's based on different neural circuits or different sets of neural circuits. So if we go back to this figure, this is implying that there's a neural circuitry to this action, and that has a certain time scale. And the time scale is based on connectivity between these areas. In mammals, this varies by species, you get wildly different, body plans or body shapes. You get different appendages that are interacting with basically the same appendages, but different, configured in different ways. So if you go from primates to bats, you have different ways that they interact with their environment. You go from bipeds to quadrupeds, and so on and so forth. But with birds, you see this, distinctly different set of neural circuits that are involved in intelligence. So, okay, let's start with this. So, it starts with humans tend to put our own intelligence on a pedestal. Our brains can do math, employ logic, explore abstractions, and think critically. But we can't claim a monopoly on thought. So there are all sorts of non-human species which have intelligent behavior, of course. A lot of birds have very intelligent behavior, and they have a different neural circuitry for this intelligent behavior. So ravens plan for the future, crows count and use tools, cockatoos open and pillage booby-trapped garbage cans, and chickadees keep track of tens of thousands of seeds cached across the landscape. So birds achieve such feats with brains that look completely different from ours. They're smaller and lack the highly organized structures that scientists associate with mammalian intelligence. And so this statement here, a bird with a 10-gram brain is doing pretty much the same as a chimp with a 400-gram brain. How is this possible? So an aside to this is the work that primatologists and biological anthropologists have done on brain size growth, or cortical growth. And so one of the ideas about why humans are so smart is that in primates, you have this growth of the cortical sheet, which when folded up forms the neocortex, or the front of the mammalian brain. And so in primates, you see a growth of this from monkeys to great apes to humans to hominids. And so this grows by quite a bit. And the idea was that, that the growth of the sheet is responsible, or the expansion of the sheet in terms of its size is responsible for, increases in intelligence. And so, you can make statements about the relative intelligence of different primates and what they were able to do behaviorally. But of course, the problem with that is that it assumes a certain neural architecture is responsible for this intelligence. And so what they're showing here is that birds have a different organization. They actually have an expanded pallium instead of an expanded neocortex. And they can do a lot of the same things, at least in terms of planning and maybe this sort of metacognition, where they're actually reflecting on their own learning and they're doing things, acting. So researchers have long debated about the relationship between avian and mammalian intelligences. One possibility is that intelligence in vertebrates, animals with backbones, including mammals and birds, evolved once. So there's this idea that you have that mammals and birds have a common ancestor, that in that common ancestor, you get the evolution of intelligence, and that intelligence diversifies in birds and diversifies in mammals in different ways, which is, a hypothesis, right? In this case, both groups would have inherited a complex set of neural pathways that support cognition from a common ancestor. And, you should see actually homologies between these two. So they shouldn't look that radically different. They should just maybe emphasize different things. And of course, we don't necessarily see that. It's hard to say what, if these regions are homologous. I mean, we don't think they're homologous. People have done a lot of work on this. But basically, the question is whether or not this intelligence comes from a common ancestor. Okay, so the other possibility then is that the kinds of neural circuits that support vertebrate intelligence and bird intelligence evolved independently. So bird intelligence has one set of mechanisms, vertebrate intelligence has another set of mechanisms, Neither of those are particularly homologous. They are an example of parallel evolution, where you get a specific type of function from multiple sources. So they may have had a common ancestor, but that common ancestor didn't have sort of the basis for intelligence as things evolved independently. It's hard to track down which path evolution took, given that any trace of the ancient ancestor's actual brain vanished in a geologic blink. So yeah, you can do things like get endocasts, but it's hard to really make any sort of statement about what those ancient brains looked like, and especially how they behave, how those brains gave an output of behavior. So you can only kind of make inferences from extant species and the sort of the brain structure that you can get from endocasts, and it's kind of a tough business, and it's really not going to answer this basic question. Okay, so you can actually take approaches such as comparing brain structures in adult and developing animals to piece together how this kind of neurobiological complexity might have emerged. So this article points to some studies. So there's this series of studies published in Science in February that provide the best evidence yet that birds and mammals did not inherit the neural pathways that generate intelligence from a common ancestor, but rather evolved them independently. So this study here, in particular, or actually I think this is describing the studies, this is Constrained Roads to Complex Brains. Neural development and brain circuit evolution converged in birds and mammals. And so this talks about these articles where they're talking about this evidence for this convergent evolution hypothesis. So again, we think that one of the drivers of intelligence, or the evolution of intelligence, is this arms race for survival, where you have competition and you try to out-survive your competition. So you grow structures of ever-increasing size, or structures of ever-increasing complexity. And so this is one hypothesis for why you would see the evolution of intelligence. You need it, you need to use it, and you need to outwit the rest of the natural world. And so that's what they refer to by arms race. They say that highly intelligent biological systems have emerged only a few times. And this is, of course, excluding insects, which we can not get into here because it's, that they also exhibit a lot of highly intelligent behavior. But that's known to be an independent origin. Among vertebrates, mammals and birds can solve complex problems, use tools, and engage in elaborate social behaviors. So this is their standard for highly intelligent, having tool use, social behaviors, and being able to solve complex problems. These sophisticated tasks involve the Pallium, the brain region most implicated in cognition, which includes the neocortex in mammals. So this is the point I mentioned earlier, that there's this region called the Pallium that is in mammals, it's like underneath the neocortex. And you have, I guess some neuroanatomists consider the Pallium and neocortex to be contiguous. But in mammals, you have the neocortex on top and it's expanded. In birds, you have the Pallium that's expanded, and the neocortex that they have is not expanded. And so there's this difference in sort of the neural architecture. There are also differences in the centers that are kind of highlighted as the hallmarks of intelligence. So there's a difference in anatomical difference, a functional difference. And so there is this kind of, evidence for parallel evolution. We're using different structures. The structures have evolved in different ways. However, it is unclear whether complex brains evolved multiple times through similar or different mechanisms. We don't know if similar mechanisms were responsible for this convergent evolution, or different mechanisms were responsible for this convergent evolution. So they talk a couple of articles here: Zarembra et al., Hecker et al., Radha Lena et al. respectively, provide evidence for the convergent development and evolution of neurons and their connection in the bird, mammalian Pallia, highlighting the need for multiple perspectives and brain comparative studies. So this is where, again, you have these structures that are very similar. They don't necessarily evolve intelligence and the common ancestor, but they have the same mechanisms that allow intelligence to evolve in different parts of the phylogeny of birds and mammals. Okay, so there's some related research articles here. The evolutionary convergence of sensory circuits in the Pallium of amniotes. Enhancer-driven cell type comparisons reveal similarities between mammalian and bird Pallium, and then developmental origins and evolution of pallial cell types and structures in birds. So they're actually doing some developmental research here as well as evolutionary research. All right, this suggests that vertebrate intelligence arose not once but multiple times. Still, their neural complexity didn't evolve in wildly different directions. Avian and mammalian brains display surprisingly similar circuits. Not identical, but similar. It's a milestone in the quest to understand and to integrate the different ideas about the evolution of vertebrate intelligence. The findings emerge in a world enraptured by artificial forms of intelligence. They could teach us something about how complex circuits in our own brains evolved. And it might help us step away from the idea that we are the best creatures in the world, especially in terms of to model artificial intelligence on. We are not the optimal solution to intelligence. So birds have this other model of intelligence. In fact, other mammals have, can be highly intelligent as well, and that's something that is, I don't have the study in, I'm not going to get into those distinctions, but that's another discussion we could have as well. But the idea here that I kind of want to draw out is that artificial intelligence is really based on kind of human intelligence, what humans do well, and so forth. And so any other sort of type of other system where you have different things that are emphasized, different structures that are emphasized, different behaviors that are emphasized, aren't really captured in artificial models. So, so there was this bias against studying birds. They lacked anything resembling a neocortex, and people simply thought that they weren't that smart because of it. And so for the longest time, it was thought that this is the center of cognition, and you need this kind of anatomy to develop advanced cognitive abilities, and they're referring to the neocortex. So, intelligence research for many years was very neocortex-centric, and so they didn't really want to use birds as a model system. Harvey Carton is pictured here. He was one of the pioneers in looking at avian neural circuits and how those neural circuits actually produce quite intelligent behavior. And so kind of getting into, avian anatomy or avian neural circuits, rather than neat layers, birds have unspecified balls of neurons without landmarks or distinctions. These structures compelled neuroanatomists a century ago to suggest that much of bird behavior is reflexive instead of reflective, I guess, and not driven by learning and decision making. This implies that what a mammal can learn easily, a bird will never learn. And so that's obviously not the case as we've seen in subsequent years. This conventional thinking started to change in the 1960s when Harvey Carton mapped and compared brain circuits in mammals and pigeons, and later in owls, chickens, and other birds. What he found was a surprise. The brain regions thought to be involved only in reflexive movements were built from neural circuits, networks of interconnected neurons. So they had this sort of assumption about what kinds of behaviors were possible with a certain type of neuroanatomy, and Harvey Carton showed that you didn't, that you could actually get from this different type of neural circuit behaviors that weren't simply reflexive. And so and they actually, because you have these network of interconnected neurons, they resembled what you see in the mammalian neocortex. And those were the mechanisms maybe of intelligence rather than the neural circuit itself. This region in the bird brain, the dorsal ventricular ridge, or DVR, seems to be comparable to a neocortex. It just didn't look like it. So it didn't look like it, but it shared sort of the cellular components, or similar cellular components, similar synaptic components, and so forth. In 1969, Carton wrote a very influential paper that completely changed the discussion in the field. His work was really revolutionary. He concluded that because avian and mammalian circuits are similar, they were inherited from a common ancestor. So this is where we get this common ancestry hypothesis. So this is the original paper here, the organization of the alien telencephalon, and some speculations on the phylogeny of the amniotencephalon. This is where he's making this connection between the structure called the telencephalon and the between avians and mammals. Now, this of course, these new papers are kind of working against the assumptions of Harvey Carton, at least the ones about the source of intelligence and evolution. So a few decades later, Luis Pugliese, an anatomist at the University of Murcia in Spain, drew the opposite conclusion to Carton. By comparing embryos at various stages of development, he found that the mammalian neocortex and the avian DVR, so these are the two sort of homologous structures, or at least hypothesized to be homologous, developed from distinct areas of the embryo's pallium. So they're looking at embryogenesis, and they're looking at the source of these different so-called homologous structures. But they develop from distinct areas of an embryo's pallium, a brain region shared by all vertebrates. He concluded that the structures must have evolved independently. So again, looking at different types of data can tell you some different things about, the source of these things, especially in terms of evolution. We can look at like anatomical data or molecular data or developmental data and reach different conclusions. So Carton and Pugliese were given completely different answers to the big question. The debate continued for decades. During this time, biologists also began to appreciate bird intelligence, starting with their studies of Alex and African gray parrot. However, neither group seemed to want to resolve the discrepancy between the two theories and how vertebrate palliums evolved. They kept working on their own method. One camp continued to compare the circuitry in adult vertebrate brains, the other focused on embryonic development. So this is where you have these two different sources of evidence that are giving conflicting answers. And so in these new studies, we tried to put everything together. Okay, so that's great. But then we have molecular data. So two new studies, which were conducted by independent teams of researchers, relied on the same powerful tool for identifying cell types, known as single-cell RNA sequencing. So using scRNA-seq, we're able to compare neuronal circuits as Carton did, not only in adult brains, but all the way through embryonic development. In this way, they could see where the cells started growing in the embryo and where they ended up in the mature animal. So this is where you can trace cells' migration through the developmental process, their origin, and how they ended up in different structures, both in mammals and in avians. So you can get a sense of what's being expressed in the different cells, and find source cells that kind of express the same things as the ones at their destination. So for their study, Garcia Moreno and his team wanted to watch how brain circuitry develops. Using RNA sequencing and other techniques, they tracked cells in the palliums of chickens, mice, and geckos at various embryonic stages to timestamp when different types of neurons were generated and where they matured. Okay, so they're able to use this timestamp method. They found that the mature circuits look remarkably alike across animals, just as Carton and others had noted, but they were built differently. The circuits that compose the mammalian neocortex and avian DVR developed at different times, in different orders, and in different regions of the brain. So this is this figure here. This describes this common neural pathway. So in birds and mammals, the neural pathways that underlie complex cognition are the same. Both process sensory inputs and output information to motor centers to drive behavior. So like we saw with this figure here, we have, an input, sensory input, gets processed, and then it goes down the spinal cord and out into the effectors. So this is the kind of the mapping, this neural pathway. We start with the thalamus, which is a deep structure underneath the pallium and neocortex that sends signals from sensory organs to the part where things get processed. So you start with the thalamus, you go to the input neurons, you go to integrator neurons, and then to output neurons. So you have these three layers of neurons. Input neurons that take things in from the thalamus, places where that information gets integrated, and then an output layer of neurons that then sends connections to motor centers. So down to the spinal cord, down to the like the arms and the legs, or different effector organs. So this is the basic neural pathway. You see this in bird brains, you see this in mammal brains. So, however, in each class, these pathways are also located in different brain regions. So in birds, we have the dorsal ventricular ridge, or DVR, and in mammals, we have the neocortex. So this is the DVR in bird brains, and this is the neocortex in mammalian brains. So you can see that there's this difference in it's kind of the location. And then we see here as a close-up, we have these input neurons here, integrator neurons, and output neurons. So coming from the thalamus, 1, 2, 3, and then back out. In the mammalian brain, we have neocortex doing the same thing. We have a similar set of neuron types in this neural pathway: input, integrator, and output, and then it goes back out down to the spinal cord. So from thalamus to spinal cord, we have this loop where we have these three different types of neuron. Okay, so that's and so this is the paper here. I think this is the Garcia Moreno paper. This is evolutionary convergence of sensory circuits in the Pallium of amniotes. So this is the study here where they do, I guess, the RNA-seq, and they use different techniques to give this data. So they have, okay, so let's see. Rohira, Elena et al. Integrated transcriptional analysis at single-cell resolution and mathematical modeling to investigate the development of sensory circuits in chicken, gecko, and mouse. Zaremba et al., which is a different paper, generated a spatially resolved cell atlas in chicken Pallium and compared it with mouse, 2 lizards, and a turtle to interrogate the conservation of cell states. So they're adding in the lizards and turtle because they want outgroups. So in a lot of phylogenetic analysis, you want the nearest set of taxa that are sort of related to the common ancestor by another common ancestor, a deeper common ancestor. And so you'll find these examples of lizards and amphibians, which will give you a sense of, an outgroup. So this is, they're using a spatially resolved cell atlas to interrogate the conservation of cell states, to see if those cellular states are, common to the bird and mammalian common ancestor, if they exist deeper in the tree of life, or if they are independently derived. Pecker et al. Developed deep learning models to identify shared and divergent regulatory signatures across telencephalon cell types in chicken, human, and mouse. So this again is where we have comparing different mammals with an avian and seeing if we have these regulatory signatures. How divergent are they? How shared are they? So these studies together increase our understanding of the evolution and development of the amniote brain. Okay, so amniotes are all animals with an amniotic sac. So this is the sort of the level, and then within that you have avians and mammals. Okay, we're here. Okay, so that's the figure here. I wanted to point that out. Then they talk more about the RNA-seq. They talk about how these papers all taken together provide the clearest evidence yet that birds and mammals independently evolved brain regions for complex cognition, and that there's this independent evolution of these structures, and therefore there's some independent evolution of intelligence or intelligent behavior. Still, it seems likely there was some inheritance from a common ancestor. In the third study that uses deep learning, this is the deep learning technique that they applied that we talked about. Kempnick and his co-author Nikolai Hecker found that mice, chickens, and humans share some stretches of DNA that influence the development of neocortex or DVR, suggesting that similar genetic tools are at work in both types of animals. So they may not share the cell signatures, they may not share the same pathways, but there are regulatory sequences that are common and so would lead to these kind of similar pathways being formed, similar cell types being formed, and thus similar types of intelligence. And as previous studies have suggested, the research groups found that inhibitory neurons, or those that silence and modulate neural signals, were conserved across birds and mammals. So again, they have these inhibitory neurons. And the important thing about inhibitory neurons is it sort of tunes or shapes intelligent behavior. So we talk about reflexive behavior. That's where you have a neural signal that kind of responds to some stimulus. But it's not just as simple as responding to a stimulus. You need a lot of inhibitory neurons that control different neural signals. So you can have things like smooth movements, or things that behaviors that aren't reflexive. You can have metacognition basically, and inhibitory neurons play a role. So these findings haven't completely resolved the debate, but I think they were kind of saying that in these studies, the takeaway is that both of them were right, none of them were wrong, which is, kind of a weaselly way to look at it, maybe, but so the next part is how to build intelligence. So intelligence doesn't come with an instruction manual. It is hard to define. There are no ideal steps towards it, and it doesn't have an optimal design. You can have innovations in evolution, whether in terms of genetic regulation, new neuron types, new circuits, or new brain regions. So this is kind of, and then we have to connect that to behavior, what kinds of behavior it generates. One of the reasons I kind of like these papers is that really highlight a lot of differences. It allows you to say what are the different neural solutions that these organisms have come up with to solve similar problems of living in a complex world and being able to adapt in a rapidly changing terrestrial environment. So this again is where you have these structures that lead to different neural solutions that solve similar problems, more or less, and they respond to the environment. They're able to adapt. So again, we have other examples in invertebrates. We have octopuses and squids having structures that allow for complex intelligent behavior. We, of course, have social insects. We have birds, bats, and insects all kind of taking to the skies on their own. So these are all things that we see many different places where intelligent behavior evolves multiple times. And again, depending on how we describe intelligent behavior, we have all of these different types of solutions. And what really counts here is that anatomy is basically putting solutions out there. Behaviors are being generated. And then those behaviors are sort of the basis, maybe for metacognition, maybe for, engaging in this arms race that increases the size and scope of the anatomy. So it's kind of an interesting way to look at intelligence. Similarly, there's limited degrees of freedom in which you can generate an intelligent brain, at least within vertebrates. Drift outside the realm of vertebrates, however, and you can generate an intelligent brain in much weirder ways. So it's a Wild West. Octopuses, for example, evolved intelligence in a way that's completely independent. Their cognitive structures look nothing like ours, except that they're built from the same broad type of cell, the neuron. Yeah, octopuses have been caught performing incredible feats, such as escaping aquarium tanks, solving puzzles, unscrewing jar lids, and carrying shells as shields. So, how did octopuses evolve intelligence using these divergent neural structures? And if we could figure that out, it might be possible to pinpoint any absolute constraints on involving intelligence across all animal species. And so, we could maybe ask some questions about intelligence in different ways if we consider all the different types of intelligences. And we're talking about across animals, so we're not getting into anything like plant cognition or any of these other things that you might think of. Or artificial intelligence. Just think about an animal intelligence. So we need to kind of think about these shared features, and they're not that it's not that they're not that they share a common ancestry, although all animals do share a common ancestry. It's that these solutions keep cropping up in different ways, again and again in the animal kingdom. So they may share maybe a common set of mechanisms that underlie these solutions. And so that's kind of what maybe we want to look at. So such findings could eventually reveal shared features, and we can ask questions like, what are the building blocks of a brain that can think critically, use tools or form abstract ideas? So what are the cells that need to be there? What are the cellular relationships? What are the genetic regulatory networks that need to be in place within the cells? And how is that all put together? And they may be put together in different ways, but those are the building blocks. And we could also understand, I think we could probably improve artificial intelligence. They say it might help in the search for extraterrestrial intelligence, although it's hard to say why that would be relevant. For example, the way we currently think about using insights from evolution to improve AI is very anthropocentric. I would be really curious to see if we could build like artificial intelligence from a bird perspective. How does a bird think? Can we mimic that? So that's that article. I like it because it does give that alternate view of intelligence. And it asks the question, or poses the question, can we model intelligence? We find sort of the building blocks of intelligence. Can we model that in different ways and generate different forms of intelligence? And then, use that as sort of our model instead of kind of assuming a rational decision-making model or a rational cognitive model or something else. And of course, our computational models would look vastly different if we considered it from that perspective. So, if we said, okay, we want to look at an octopus intelligence or bird intelligence, how does that differ from a human or a mammalian intelligence? And then what is the way that what kinds of models can we use? It's very different. Okay. We have some things in the chat. Okay. So are there any questions about that?
Sorry, Bradley. I'm currently in the car.
Okay.
But no, I was just yeah. I mean, I saw this article too, and you know, it just makes me think of the the new understanding in evolution that you can have, you know, similar structures kind of re-emerge multiple times.
Yeah.
And they don't have to be related. Yeah. Anyway, as well as, like, you know, all the terrific work that's gone on with bird learning. Yeah.
Yeah, that's great. And then, of course, the idea that, you know, do we have like common building blocks across different types of intelligence? That's another interesting thing.
Right. I mean, like yeah, for sure. Yeah. All the Levin-like arguments.
Yeah. Yeah. So one of the things that we were talking about a while back is that, you know, going through these kind of definitions of intelligence, where, you know, people have defined it kind of largely from a behavioral standpoint, you know, kind of thinking about what it is and how to clearly define it. And we, you know, had gone through the literature a bit and found that it's as clear as mud, really. And the definitions are not very, you know, there are many competing schools of thought. They're kind of based on, you know, very limited aspects of behavior and things like that. So I'm just thinking, as I was reading through that article, I was thinking about how you might define kind of intelligence in terms of like these sorts of mechanisms that lead to intelligence, or, you know, the actual behaviors themselves. So I like in that figure, they showed the circuitry. And they showed then birds and humans, you have the same circuitry, where you have like 3 layers of neuronal types. And then you also have these inhibitory neurons in there. So those seem to be maybe key to producing certain types of behavior. And so it's kind of an abstract definition on the one hand. It wouldn't necessarily be useful for like a psychologist, but it would be useful for someone building an artificial intelligence, because then you could specify what kinds of parts you would need for, say, like it could be a neural network, it could be like some sort of reservoir network or whatever. And you could put those pieces together and say, okay, we have those parts. And in fact, you know, kind of the way that neural networks work, as much as they're not necessarily a model of the biology, you see those same maybe sorts of things happening there. You have like a hidden layer, and you have, you know, maybe your 3-layer networks. You have multiple layers. In some cases, for deep learning, you have many layers. And so maybe that's what's key to intelligence, isn't really like the behavioral definition. It's like these parts. And then when you get the parts in place and you can configure them in different ways, the behaviors just kind of get generated. And it's, you know, then a matter of what environment that the intelligence is in. It's sort of its history of interacting with the world. It's sort of history of observing data and refining its answers from data and things like that. And then its ability to do that. So if it can't select things from the environment properly, then it can't really, it's not intelligent. I mean, if you have like, if you're just parroting back every answer that you generate, then that's not really intelligence. It's kind of refining that to a point. And so, yeah, I don't know. I don't know what the answer is, but I think that's kind of interesting. Yeah, definitions of intelligence, and we had a definition in the first paper that was interesting. But there are a lot of definitions, as I said. Okay, so that's good. Go ahead, Morgan.
No, I was just gonna say, it's really interesting to look at the people studying octopuses and who have these same debates and these same issues of how best to measure it, or how best to well, what I like is to use the AI term, how best to benchmark them.
Oh yeah. Yeah, I think that's actually a good term for what we're talking about here, because you have a lot of different you have a lot of different behaviors that have like some similarities. Like if you were to say, okay, problem solving in mammals, problem solving in birds, problem solving in octopus, go, and then you compare the solutions, and it might be comparable, but it's best to sort of benchmark them in some way. Like if I have this certain neural architecture, here's the performance on these different tasks. They're not directly comparable. Some architectures are going to be better at some tasks than others, and you could make a table. And then you could say, okay, well, my octopus-like intelligence benchmarks well on these tests. My mammalian-like intelligence is better in these tasks, and so forth. And you could say, well, do I want an octopus-like intelligence or a mammalian-like intelligence, and for this task, for this thing that I'm using. You could open source the models and everything. So. Okay. Well, that's fun to think about. Last thing I wanted to talk about today was to finish up with this paper here, and this is kind of an extension of what we've been talking about. This is kind of getting into, and I don't have any papers right now on the octopus intelligence. Maybe I'll try to do that next week or follow up on this with the discussion. But this is a paper on avian cognition, or the evolution of avian intelligence. And it's a review paper from 2006 called Cognitive Ornithology. So it's the study of bird cognition or avian intelligence. And so this is about comparative psychology. So there's this area of comparative psychology where, psychologists will compare different animal species with humans and get a sense of what that, they'll use that as sort of a way to gauge the evolution of intelligence. So a lot of comparative psychologists interested in the evolution of intelligence have focused their attention on social primates, whereas birds tend to be used as models of associative learning, which is interesting that they have these different types of behaviors that they look at in different species. However, corvids and parrots, which have forebrains relatively the same size as apes, live in complex social groups and have a long developmental period before becoming independent. So this is like in primates, especially humans. One of the hallmarks of a bigger brain in primates is that you have this longer developmental period. The thinking is that you need these complex social groups to interact with to become, to fully mature. And when you're mature, you're much more intelligent than species with smaller brains. Okay, so that's, and then so there's this long developmental period, complex social groups, and these corvids and parrots have demonstrated ape-like intelligence as a result. Ornithologists have documented thousands of hours observing birds in their natural habitat. They have focused their attention on avian behavior and ecology rather than intelligence. So this review discusses recent studies on avian cognition, contrasting two different approaches. The anthropocentric approach, which is where we view intelligence from sort of a human perspective, how different is human cognition from that of birds. And then the adaptive specialization approach, which is where you think about cognition as a series of adaptive specializations, and thus intelligence as a set of adaptive specializations. It is argued that the most productive method is to combine the two approaches. This is discussed with respect to recent investigations of two supposedly unique aspects of human cognition. The first is episodic memory, and the second is theory of mind. And so this is where, people throw this term theory of mind around a lot in AI. But basically it's where you have an intelligence that can think about what other intelligences are thinking. So this is where, you have a social group. I'm an individual. I can think about what another individual in the group is thinking about and model that behavior. So it's kind of like a metacognition, except it's in a different mind or a different brain. And so these are this is, at one time people thought this was unique to humans, and there's been some kind of debate as to whether it's much more expansive across animals or not. And, some of the tests of theory of mind in animals have been kind of questionable. So this is part of the controversy. But basically, it's the ability for an animal species to have individuals that can think about what other individuals are thinking about. And of course, extending that to artificial intelligence, it's even more questionable as to how that's applied. But anyways, episodic memory, of course, is the memory of different episodes and being able to recall them. So those are usually thought of as unique aspects of human cognition. In reviewing the evidence for avian intelligence, however, corvids and parrots appear to be cognitively superior to other birds, and in many cases even apes. This suggests that complex cognition has evolved in species with very different brains, or a process of convergent evolution rather than shared ancestry. Although the notion that birds and mammals may share a common neural connectivity pattern is discussed. So this is all stuff that we talked about in the last paper. And so, again, this is kind of moving us away from this anthropocentric view of intelligence and towards this sort of view of intelligence where you have different intelligences that evolve in different clades of the tree of life, and they have maybe they have similar building blocks, but they're expressed in different ways. They may be behavioral, but they're definitely different neural architectures. So this is kind of talking about bird brains and how neocortex is basically the 6-layered structure where you have processing that goes from the bottom to the top of the neocortex, and each layer has some processing step. This is the basis, of course, for the cortical columns that they use in Numenta's computational models. So this is something that is this 6-layer cortex is, you find it in birds, you find it in a lot of vertebrates, but it's most highly expressed in mammals and especially in primates, where it's expanded quite a bit, and you have this sort of processing power that is thought to be sort of the seat of cognition or complex cognition. So the idea that the 6-layer neocortex of most mammals is the prerequisite for complex cognition, and this still pervades popular culture. So the idea that you need this 6-layer neocortical structure is, of course, the basis for Numenta's model of intelligence, but it's also sort of this idea that, you're capturing basically intelligence with the structure, and that you need to move towards a structure to get the result. Let's see. So some, a lot of comparative psychologists and neuroscientists also hold this sort of bias for six-layered cortex. One reason for this long-held but ultimately incorrect view is that confusing terminology used to name the different regions, the avian telencephalon or forebrain, is basically to confuse the striatum, which is the part that's enlarged in avian cerebrum, with sort of these parts of the basal ganglia, which are involved in these more reflexive behaviors. So as the vertebrate basal ganglia is involved in species-specific behaviors, such as maternal care, sexual behavior, and feeding, bird brains were deemed incapable of producing flexible or intelligent behavior. It is now known that this nomenclature is based on a fallacy. Large parts of avian forebrain are derived not from the striatum per se, but from the pallium. So this is the part that's enlarged. And so they actually kind of thought that the striatum was really the part that was driving the intelligence of the pallium. Interesting, the mammalian neocortex is also derived from the pallium. This places the avian forebrain into a new light, where bird behavior may now be explained as an adaptation to solving socio-ecological problems similar to mammals, possessing hardware that is different from mammals, albeit evolved from the same structure. So this is kind of what we look at when we look at, and sometimes when we look at animal intelligence or comparative cognition, we often look at the size of the structure as generating the intelligence versus body size. So these scalings, you'll find these for neocortex when you're looking at mammals, especially primates. You'll have the volume of the neocortex versus body size. So the larger the neocortex is relative to body size, the more intelligent the species, presumably. So you'll see this plot in primates where monkeys have a small neocortex volume relative to body size, and hominids have the largest neocortical volume with respect to body size. In birds, you actually have a similar relationship between the telencephalon, which is the volume of the telencephalon, with body size. So you have these smaller birds that have a smaller body size, and they have a smaller telencephalon. And of course, you'd expect that as the body size grows, the telencephalon volume would also grow. So in different species that are bigger, they're going to have corresponding anatomical parts that are also bigger, but they should scale 1 to 1. When you have an expanded structure, that means that that structure will scale nonlinearly, or maybe 2 to 1, or 3 to 1, or whatever. And so you see this in a couple of species. You see in the rook, for example, the telencephalon volume is much larger than the body size gain. So as the body size grows, the telencephalon grows at a positively nonlinear rate. You have other species like the magpie, which have a large telencephalon relative to body size, and the jackdaw and some other species as well. So you see that there's this scaling that we use to sort of look at the size of this enlarged structure relative to body size, and where that structure is nonlinearly positively enlarged relative to body size are the species that we're interested in. Okay, and so just kind of thinking about intelligence from this sort of evolutionary ecologic perspective, and this is why we use these kind of scaling laws to sort of find, where brains have enlarged. We can actually look at maybe some of the links between the forebrain size and how that's large relative to body size and how that relates to behavior. So consistently, there was a significant relationship between high innovation rate and large relative brain size for corvids, parrots, and to a lesser extent non-corvid songbirds, woodpeckers. hornbills, owls, and falcons. These patterns were similar, and when frequency of tool use was also correlated with the relative brain size. So again, you have these behaviors, these intelligent behaviors that correlate with the brain size. The enlargement of the brains relative to the body size that's kind of what's driving this. And then birds have also adapted to solving other types of socio-ecological problems. So, for example, living in large individualized societies, where group members recognize one another, have long-term relationships, and track other social relationships, and therefore require specialized neural systems to process such types of information. Okay. And then, of course, concepts and categorization, where birds, like in mammals, especially primates, are exceptionally skilled at discriminating between visual images. Such images can be categorized based on their perceptual similarities, or may even be grouped together based on a human-like abstract concept, such as same, different. So pigeons, for example, can discriminate images of aerial photography or aerial photographs. Pigeons, trees and water, chairs, cars, humans, and flowers, and even arbitrary stimuli, such as letters of the alphabet. So they can do this kind of discrimination. They don't necessarily attach a symbolic meaning to it, but they do this sort of, they can distinguish between different types of stimuli. And then, of course, they can do other things, transitive inference, role versus rote learning, insight learning and problem solving, numerical concepts, object permanence. So we have all these different aspects that bird brains can do just as well or on a comparable level to mammalian brains, particularly primate brains. So I think that's all for today. Thank you for attending. See you next week.